To find the speed of sound when we know the temperature, we're going to use the new formula. So that is 331 plus 0.6 times the temperature, and that T, we like to write that degrees Celsius to remind us that it's not the period. And so we take 331 plus 0.6 times 3 degrees, and this comes out to be 332.8 meters per second. And now we can use that value of V the way we've used it in other situations. So in the next question, calculate the wavelength produced by a 356 hertz tuning fork. So we're looking for the wavelength, which is lambda. So we would choose our formula that involves lambda, and we again would use this speed that we have here. That's 332.8, our frequency, and then we solve for our wavelength. All right, so all the things that we have been doing the last week or so, we can continue doing them. We just have a new way of finding our speed. Let's look at the temperature is a little higher. All right, so it's the same formula. I'm not going to rewrite it again. We would take 331 plus 0.6 times 37. All right, and a higher temperature gives us a faster speed for those waves. This ends up being 353.2. And so now, when we use the setup that we used previously here, so speed equals frequency times wavelength. All right, so now our wavelength is 0.992 meters. So we can see that the wavelength increased when the temperature increased. All right, so that's the indication that this is a direct relationship. All right, so this is a direct relationship. Excuse my scribbles here. How did I know that? Because as V increased, lambda also increased. Okay, so when you see two quantities both changing in the same way, that is a direct relationship. Inverse, one goes up, one goes down. All right, let's look at one more. So in this case, we've got some information. This is similar to something we've done in the past. It's actually a question off of a previous quiz. So the waves are moving across this concert hall that's 120 meters long in a certain amount of time, 0.343 seconds. And so we can go to an old idea for wave speed, okay? So it doesn't always have to be that new formula. We still have all of our other formulas as well. So in this case, it's a specific distance that the waves travel in a specific amount of time. And so we can say distance over time, 120 meters divided by 0.343 seconds, and we get a speed of 350, about. I rounded that a little bit. All right, so our values, even though we're using a different method, we should still get a value for the speed of sound that sort of makes sense, that's in that like middle of the 300s sort of a range. Now we could work backwards and we can find what the temperature is. So if I use this equation here involving temperature, I can put in my 350. I can then notice that the only thing I don't know is that temperature, and so then I could, subtract 331 from both sides, find that, divide by 0.6, and we would get our temperature, and this is 31.7 degrees Celsius. Okay, so make sure you label the temperature units, degrees Celsius. We could also instead, again, use this speed that we just found to find something like frequency. Okay, so again, don't lose our old skills. V equals F times lambda. In this case here, we were told that the lambda value is 0.4, and so we can solve for F in this problem. All right, and a reminder that frequency is measured in hertz, so that would be 875 hertz. Divide both sides by 0.4. And again, an old idea, find the period of the sound waves. All right, so period is 1 over the frequency. All right, and so we get a very tiny number. Okay, this is a really high frequency, so it doesn't take very much time to make one cycle, 0.00114 seconds.